All right, good morning, everyone. Today I'm not properly moving into something new today, but I am just reminding ourselves of where we are in the course as we approach the midpoint of the term. We've talked a lot about loads on structures, and the first two assignments have been about loads on structures. So assignment 1 was gravity loads, assignment 2 was lateral loads. You did some structural analysis. And assignment 3 is all about the tension members. And so you're going to design some tension members for the maximum factored tension force that you would have, well, you have to calculate the maximum factored tension force on assignment 3. You would take the tension from wind, earthquake, dead, live, and snow loads from the notional load effects, factor them up, and design a brace to take that factored tension force. Okay, so just so you know, I've posted my correct answers, and so for everybody's layout, I've posted some correct values for what the bottom tension force would be from all the load effects. And your goal is to start fresh with those correct values of tension in those braces, not to carry forward the values you calculated. Even if you did it correctly or reasonably, I still want everyone to start at the same point so that when you're making comparisons later on, it's not due to differences in your load calculations that you're getting different designs. It's just due to the different layouts, okay? So we've been spending a lot of time talking about tension members, with the ultimate lecture there being a design example for a bolted tension member. Today we're going to start talking about welds, and in the context of welded tension members. Okay, so we talked a lot about how tension members might fail with bolts through them. Today we're going to start talking about welds and how tension members might fail when they're welded to the gusset plate instead of being bolted. Okay, so pretty much all the same stuff that we've talked about already still applies. We're still going to have a gross section yield that we're going to calculate. It has nothing to do with how the member's connected. We're still going to have a net effective area calculation that we're going to have to do, and from time to time block shear. It seems a little bit strange now because so far we've only talked about these things when there have been bolt holes. Like you start drilling some holes through the tension member, you're going to start to have a net area because you're reducing the area of steel there. Generally, with welds, we are going to see that we don't have to drill holes, and so we get to maintain more of the net section, but there are still shear lag effects that we're going to have to talk about when we talk about welded tension members. Today is just going to serve for an introduction to welds, and I guess welding in general. Welding is a little bit more complicated than bolting. The engineer needs to know a little bit more about the similarity of metals, what the different electrodes are for, when to specify certain welds in different situations, and there are a whole bunch of symbols associated with giving instructions to the welders to actually perform the welding, and so there's a little bit more involvement on the background behind what welding is and how we specify them. We're going to look at a different set of ultimate limit states now. We're going to look at welds in shear, we're going to look at welds in tension, and groove welds. And so in particular, we're going to focus today on groove welds. We'll just see a very quick example at the end how we'd calculate the tension strength of a groove weld. Primarily, we end up using fillet welds in shear and in tension, and so next day we'll start talking about what the strength of welds in shear and tension are when we use a fillet weld. And basically, this is just serving as an introduction to what welding is, what things we have to look out for with welding, and how welds might typically fail under different kind of loading situations. Basically, after today, you should be able to describe the welding process and some of the pros and cons of welding versus bolting. Not just tension member connections, but connections in general. You should be able to differentiate between types of welds, and so we're going to talk about fillet welds, partial joint penetration welds, complete joint penetration welds, plug and slot welds, so the focus will be less on plug and slot, more so on fillet, a little bit less so on partial joint or complete joint penetration welds. You should be able to decipher basic weld symbols for groove and fillet welds, and ultimately today we'll look at calculating the resistance of a partial joint penetration weld in tension. Okay, so more high-level stuff, perhaps a little bit less technical in terms of calculations today. Does anyone have any questions about those four things and why they might be important before we get into the material this morning? All right. So I've passed around this previously, right? I'll pass around again. This is a series of two plates. It's called a lap splice. You take one plate, you lap it over the other. And these are fillet welds. And so there's a little triangle welded on the ends of the two members. this is one way you might be able to connect steel together, and it's one way we might choose to connect our tension members to the gusset plate in certain situations. But before we get into that, I have a little poll. Is this going to do this to me again? It is going to do this to me again. I'll present this on the other side then. Pull this over. Try this. And, oops, that's not the right one. What's going on here? Here we go. So I do have a word cloud here. It's going to be a little bit sketchy just because of the size of the screen here and everything. But the question here is, what do you think some advantages might be to bolting a connection? So far we talked a lot about bolted tension members. We're going to start talking today about welds. Why might you bolt? Like, why would you perhaps make a decision as the engineer to bolt a tension member perhaps instead of welding? I don't expect you to know the answers, but if you think for a minute or two, what do you think would be a reason to select bolting a connection instead of welding a connection? Oh, for God's sake. This is just, I don't know what the hell's going on with pull everywhere these days, but it is giving me the worst time. Good? Okay. Why might you choose to bolt your connections? Maybe if you wanted to accommodate some movement, there's less skill required. It's a simpler option, perhaps. Maybe it's convenient. Great flexibility, perhaps. Easier for construction. Maintenance, could be less maintenance or more flexible on the maintenance side of things. Lots of good words here. Replace. Replace is a great one. I like replace, and I'll show you an example here in a minute of how replacement was a nice option for having a bolted tension member in a specific example that I looked at when I was still working. Perhaps some variability. So that's great. Those are all great words. I think that you have the gist of it there. The next one I'm going to do, if I can actually see what it is that I'm doing here. So lots of great words there instead of welds. Weld a connection, trying to bolt it. Where are the words? There we go. Fun. Anyone? If you said fun, it's probably because you welded before, right? Like it is kind of interesting to try to do some welding. It's a fun process. Transfer of loads, better maybe, stronger maybe. What we're going to see is, like, the engineer, you can control the strength of anything, okay? So generally speaking, we'll see that, yes, to maintain strength of tension member connections with welds than it is for bolts. It looks good, maybe. This is a subjective thing. Some people might think welding looks good. Some people might think that bolting looks better. One of the nice things is that you don't get the slip, right? We talked a little bit about towards the end of our discussion on bolted tension members, and so no slip is kind of nice. We don't have attention to that serviceability limit state to potentially get slip in the connection of the tension member to the structure. It's hard, maybe some stability. We're going to see welds are actually really good at accommodating misalignment. If you drill holes in the tension member, you drill holes in the connection, you put everything together, and if your bolts holes don't line up well, like this, precise, right? You got 2 millimeters or maybe a 1/16 of an inch in all your holes to try and align everything, and so it may actually be difficult to deal with alignment issues when you're bolting things than it would be to deal with misalignment if you're welding things together. Okay, so that was fun. Generally speaking, the things that come to mind for me when selecting is welding, bolting, pros and some cons here. It's preferred to do in the field. If you can get everything to align properly, it takes a lot less time to actually make the connection. You put the bolts in, you torque it. Doesn't take a high level of skill. You don't have to lift the welding machine into the air, and the quality control issues are generally fewer when it comes to bolting. You bolt it, you tighten it, it's done. Make some pretty bad welds, especially when you're doing it in the field. So it requires less training to install. There's a lot less variability in strength. Welding is basically the installment of material that's controlled by an electric arc, and we'll talk about that in a bit. There's more variability in the strength and geometry of welds, which generally means we get a lower resistance factor when calculating the strength. You can always remove that member if you need to. If you weld it to something else, you've got to grind it out, and you have to get a hot work permit, and that gets really annoying. But if you've bolted it, you can just undo the bolts and remove the member if you need to for some reason, and put them back. Welding can accommodate more misalignment in the field, and so it actually happens where they might specify a bolted connection. Like, we can't line up in the field. They're trying to put the brace in, can't fit. What they do instead is they'll bolt one side, they'll weld the other side with the misalignment issue. It generally maintains the net section because we're not drilling holes through them, but and so generally we can get a stiffer connection. We don't have to deal with that slip serviceability limit state. They can slip in the holes, they can reduce the area and tension, and they're not as easy to accommodate alignment. And welds have higher variability, takes more time and inspection. You need trained professionals, and you have to cut and grind welds if you're going to try to remove any of the particular reason. Okay, removability for me is quite important, and it's quite important to folks who work in the heavy industry. For example, I was working on a project once where the pulp and paper mill, they were upgrading to sort the size of wood chips to generate the pulp that they produce at the pulp mill. And the only spending several hundred thousands of dollars was to remove the bracing that was here. And so the only way that they could get this machine in was to remove this metal panel siding, remove it early so that they could crane those chip screens into place. You have to have a really sharp pencil and know what you're doing to approve the removal of bracing in a structure, but you can generally make it work. We talked in lab that other day when we were playing with the MOLA kit. Bracing on at least 3 sides of the building, you can maintain stability, and you don't expect a 1 in 50-year windstorm during a 7-day maintenance. Generally, you can make that work. And the only reason they can make that work was, you can see here, they've got some bolt holes. They basically pop the bolts out in place and then put the bracing back into position, save them a lot of time and a lot of money during a maintenance shutdown. Okay, does anyone have any questions about why we might prefer bolts or welds before we continue on? So we're going to talk about the arc welding process. There are lots of ways to weld things. Welding, you can do, I don't know, a bunch of other kinds of welding, but generally speaking, structural welds are done by arc welding. What arc welding is you basically run a voltage with a certain level of amperage and power source, so you plug into the wall. Normally it's DC for welding, but depending on working with alternating current or direct current. And basically, you have a power source, you connect you're working with, and the only way you close that circuit and actually have the amperage flow through the system is what's called the electrode to the that you're working with. Okay, this here is called the stick electrode. All right, so it's around. This is the electrode that goes in the holder, and so basically there's a steel core or a metal core, and it's basically when that metal starts to contact this piece of metal that you're welding that you close that loop. Levels of amperage, and that amperage generates heat, which melts the metal, and as the metals get molten, they mix, and as they cool off, they solidify to fuse those pieces together. You can do arc welding a bunch of different ways. Gas shielding, or you can do or gas or shielding to protect the molten filler. That electrode protective coating is called flux. When you weld, that flux falls off and protects the molten. Steel is molten, it can corrode very quickly. And so once it's molten, you need to protect it from corroding. For stick welding, there's a flux that shields the molten metal from oxidation. Gas that gets consistently fed through the system as well, and that gas will basically keep the oxygen away from the metal to prevent it from corroding. Okay? So basically, we're just closing a loop. The high heat generates a certain amount of heat, and that melts the metal so that they can fuse together. There are a bunch of different ways we can do this. The two most common are shielded metal arc welding. Nobody calls it shielded metal arc welding. We welding, and we call it stick welding because we use that stick, and we refer to the electrode, generally speaking, as a stick. The electrode generally comes in rods, and as you weld, that rod gets shorter and shorter and shorter. That flux goes to, and it requires frequent replacement of these sticks. So you might get able to do maybe 6 to 12 inches, maybe a little length with one stick. You pop that one out, you put a new one in, and you continue the process. Katie, you had a question? Mm-hmm. Well, yeah, this would just be like the metal, right? So this would be the base metal. I'll give you some more examples here about what's basically going on. Basic schematic of what's going on. Like I'll show you what the result of a weld looks like. But the work connected to the steel itself. And so you actually have to connect a cable to the steel that you're welding. Or a lot of times they'll use what's called the welding table. They'll make a table out of steel. They'll clamp one of the cables to the steel table, through the steel table, and then the current basically passes continuously on that circuit. Through the electrode cable to the electrode, back through the steel you're working with, through the work cable, and that loop, the loop for the current to pass through and generate the heat. So shielded metal arc welding is, whoops, what happened there? Here we go. Shielded metal arc welding is common for structural welds, though it tends to have its pros and cons. There are different kinds of electrodes. Has the electrode? Or does anybody have the stick that is passing around? Drew, can you see on the stick anything on it that tells us anything about it? Might be hard to see. It kind of tends to wear off at a certain point in time. Yeah, so there's that one says E4914. Is there another label on it? Oh, 17? Okay, so 17 or 14? 14, okay. So that's a keen eye. US there, but basically there's going to be two labels. There's going to be one that says E4914 on that specific electrode, one D14. I'll come back and talk a little bit about what those numbers mean in a minute, but basically you can choose kinds of weld material. So the core, the actual electrode material, could be a different kind of higher carbon content, lower carbon content, different amounts of minerals and metals in it for certain applications. Spring coating the flux is appropriate for protecting that specific type of metal. There's also called gas metal arc welding. Gas metal arc welding is more commonly referred to as MIG, for metal inert gas welding. Generally, the electrode, instead of coming out in a stick, there's a continuous reel of basically wire. And as you press the button to deposit the electrode, the wire continuously gets fed out. Oh, I don't know. I think it's maybe 18 gauge wire from a MIG welder. It's basically continuously gets fed out through this hose here. So the wire comes out through the hose, and as long as you're pressing this, wire will continue to be fed. Otherwise, the process is very similar. So as you deposit that wire, it starts to complete that, melts and fuses with the steel. And basically, it's a little bit more efficient because you don't have to continuously replace the sticks. It just continuously comes out in reels, several meters long, probably 100 meters long worth of wire. Stop and start and stop and start. And one of the other things that they like about it is that there's a gas that gets pushed out. So in addition to the wire, in addition to the wire coming out here, there's also a gas. And it's an inert gas that basically pushes oxygen away from the molten metal, and that's away from the molten metal and stop it from oxidizing. One of the nice differences between MIG welding is that when you deposit the flux that coats the electrode here, it's called a slag or a flux, and that basically covers the weld. And you cannot weld over that bigger one until you clean it away. You have to hammer it away and brush it away. And so it takes time to actually do the weld, replace the slag, and start to weld again. With the metal inert gas, you don't need to clean anything. You just continue because the gas just goes away. It doesn't cover the molten metal in anything that you really need to clean away. And so from an efficiency standpoint, using a metal gas is more efficient when it comes to generating a structural weld. Does anyone have any questions about the differences between SMA and GMA welding before we continue on with the rest of the stuff today? Okay, so unless you're welding yourself, you really generally don't care what kind of welding they're doing, as long as they're meeting the standards for doing structural welding. They'll generally choose whatever works best for them. What you do need to know is how you would generally specify welds to connect. The 4 common types of welds are fillet welds, and in fact this is similar to that little piece of steel. So that would be a lapped connection, and basically that's what you just saw here. So there's one plate, lapped. They come in, and with the electrode they deposit weld material. On this side, flip it around, deposit weld material. They get a connection between the 2 edges of the plate, and you have a fused connection. There's a groove weld. If instead of taking these pieces of plate and lapping them over, and instead I butted them together like this, if I butt them together and I grind some steel away on the other side, I can just basically fill that. That's what they call it when you grind away the steel on the 2 sides of the butt plates. It's a groove, and you fill that groove with weld metal. The result is a groove weld. But you might also, from time to time, do what's called a plug weld. It's kind of like a bolted holes, fill the holes with weld material. Don't use it too often. I've never actually seen a plug. And similarly, there's a slot weld. You can make a really long hole and fill that slot with weld metal, similar to a plug. And again, I've never seen or specified either of these welds personally as a structural engineer, but we work with it and groove quite often. Okay, so fillet weld is certainly the most common. And then groove welds are probably second most common. Okay. This course, we're going to focus on these. We're not going to talk about these types of welds, as well, I've never used them before, and there's not really a whole lot across one at a certain point in time. So there are lots of different ways to make these kinds of welds, and certain welds and applications. For example, a butt joint, you cannot butt 2 plates together and then fillet weld them. Do it, it's silly. And so we tend to do butt welds where we take 2 plates, we groove them and put them together with material. That would be a butt joint, and we would exclusively do that by a groove weld. If you want to make it the same pieces of steel, and instead of butting them together, you can take one, take the other, and you can put them in a T. You can either do fillet weld by welding that side, which would be on the left, or if you grind off the steel from one with a groove, you can fill that groove with weld material, and you've got a T joint. Corner joints, pretty similar to the other side, but instead of butting them together, you're butting one into the face. You can either do a fillet weld here, or you can groove one of these sides and fill the groove with weld metal to make a corner joint. And finally, there's a here. Lap joint you can only make with fillet welds. There's just no sense in making them with groove welds. I guess you could technically make them with, basically it would just be a really hard to make kind of fillet weld. Those are the typical kinds. We're going to focus, generally speaking, on welds that kind of look like this and kind of look like this, though we'll see how they get loaded when we talk about fillet welds in more detail next day. One of the things you should always think about as the engineer is construction. If you understand how welding happens and how welders do their welding, you will stay away from specifications. The easiest thing for a basic welding novice to do is to weld in the flat position. And the flat position basically just means you take the piece of steel plate, you basically put them, and it's a perfectly flat weld. The weld material is not going to spill off to one side. You don't worry about the molten material sliding. It's the easiest weld that's flat. You weld and you're done. The position is a bit more difficult, but not that much more difficult. You just have to, when you're welding, Make sure you're trying to weld towards the top of the weld so that as the molten metal slides a bit, you get an even surface. But as you start to get vertical, that's more difficult because the molten metal wants to basically fall down, right? So you have to be very careful and select certain kinds to make vertical welds work. The hardest kind is overhead, right? Imagine trying to put down molten metal on something that's over top of you, trying to weld like this. That's the most difficult weld position to take. You need a very skilled welder to perform a weld like that. And 9 times out of the 10, the engineer will specify something, thinking about it twice. And so you, as the engineer, should be thinking about, first of all, where they're going to be welding it. You can specify anything they want if they can position it in their shop and do a flat weld. But if you're in the field, there's no way to reposition the building to do a flat weld. If you're welding something and it's overhead, and that's something that the welder has to do, and it's more difficult to do that. About types of welds, when we might use fillet welds or groove welds, which are the focus of this course, and a little bit about different positions the welder will have to take in the field or in the shop, and why the engineer has to think about those things. Are there any questions about those concepts before we continue on? Okay. The next thing that you have to be very aware of electrodes that you have to work with. This is the weld electrode classification scheme. Basically, we've got a number, it's the strength, and this is where on the electrode that I passed around, you're going to see 2 different numbers. 49 means KSI. It's 49 KSI. That's the strength in kips per second, and that's an imperial designation. If we're working in megapascals, the equivalent, or sorry, that's wrong. I just got that wrong. That's 490 megapascals. Okay, so the first 2 numbers are the first 2 numbers of the ultimate strength of the weld material. And so if we're in metric, 490 MPa, and we use 49 in that designation. If we're working in kips per square inch, that's because 70 KSI is the equivalent of 490 MPa. And so imperial standard, metric standards will say E49, and so you have to know if you see E70, it doesn't mean it's 700 megapascals, it just generally means it's 70 KSI. There are what we call matching electrodes. We all the ultimate strength of the electrode that we're using is a bit higher, but not too much higher than the strength of the steel. So for 300 and 350 MPa steel, Fu is pascals. The matching electrode would be E49 or E70 because the ultimate strength, but not so much higher than the ultimate strength of the steel. And that's going to matter for strength calculations because either the weld material is going to fail or the steel that the weld is fused to is going to fail. Generally, as long as we have an electrode, we can always just work with the strength of the welds, and 9 times out of 10, you're going to be using 49 electrode with the 300 or 350W steel that we're going to be using in this course. And so it might be 1, 2, 3, or 4, or 1 might also be general. The numbers don't necessarily these numbers. It's just the code that indicates the different kinds of welding positions you can take. And the weld current. Okay, so there's different kinds of materials and different kinds of coatings. And so the first different positions. And so this electrode was E49, 4. The 1 here means that it's applicable for all positions. And so you could use this as a general electrode for flat, horizontal, vertical, or overhead. Some welding electrodes you can only use flat. And so if it was a 3 instead, we'd only be able to use a flat position weld, and that means that they can't use it for other types of welding positions. E49, 1,4. The 4 here tells us that that's a titania. It can work with AC and DC current, and that's the most common coating to protect this particular electrode from corroding. This is the most general electrode. E49, 1,4 is generally the most common. As the engineer, it's very common for us to just specify on the drawings E49XX. That leaves it to the fabricator or the welder to decide, based on the position that they're trying to weld or where they're trying to weld, what the other two numbers should be. You just specify, generally speaking, the strength. Unless, from time to time, if you're working on a brownfield site, that means stuff already exists. And there's an existing beam up there from 1950. And you know from some kind of test that it's a specific kind of steel that was made in Germany that has a really high carbon content. If you're specifying welds to that as an engineer, you need to specify a very specific kind of welding electrode here so that the weld metal is going to be compatible with that high. If you just said E49XX welder to figure it out, you'd be in trouble because that weld would fracture in almost no time. On sites with existing conditions, you have to be very careful about specifying welds. Okay. The electrode specification has the strength in it, some stuff about welding positions and coatings. Does anyone have any questions about those before we continue on? Engineer has to specify welds, and it would be great if we could just show them pictures all the time. However, not as much anymore, but we're generally, and in the past we've been limited to trying to communicate this information in drawings. There are some very specific shapes that are commonly understood to mean certain things when we're trying to. The shape we're going to use most often in this course is fillet. It's just a little triangle. Or a bevel weld to denote some kind of partial joint or complete joint penetration weld. There are some ones like we'll see that when we start talking about base plates towards the end of the course, when we might see that symbol. This is a weld that you cannot do in the shop. This is something that would have to be done in the field. And so when the people are putting stuff together, they'll know, okay, I have to wait and weld this in the field when we're putting stuff together instead of welding it in the shop. From time to time, hear about specifications about the process or any kind of other references, or maybe there's something about the specific kind to weld in the position that they're in, the location that they're welding in. But these are some going to be working most commonly with the four that are shown here in color: fillet, weld all around, and then the welds. So if we saw, for example, some symbols like this, on the left-hand side we've got some T-joints, right? That's basically something like this here, T-joint. The first symbol, we've got a fillet weld. 6 denotes the size of the fillet weld, and the triangle is actually on the bottom side of that line, denotes that the weld is on this side of the arrow. What it means is I'm going to take my electrode, I'm going to make a 6 millimeter weld on that side only. I'm going to come in here, make a weld like this, and that leg size is 6 millimeters. The next one down is 8, which means it's going to be a slightly bigger weld. And the fact that the triangle is here happen on the other side of the arrow. Okay, so this is a very specific thing about which side of the line. This means weld this side with a size of. Okay, so similar symbols meaning quite different things. Size of the line tells you where the weld is actually going to happen. What do you think triangles on both sides of the line means? Both, right? So we're going to weld this side, they're going to weld that side, and so triangles on both sides to do something like this, something like that. And then we've got, when it comes to groove welds. Groove welds are kind of difficult to specify. There's going to be one kind of groove weld, penetration weld, and then there's also going to be one called a partial joint penetration weld. And I'm actually missing some information on my partial joint penetration weld, but I'll talk about that in a second. CJP basically means I weld to completely fill the joint from top to bottom. And so I've got a plate that's, I don't know, millimeters, I don't know. The weld metal should go all the way through the entire joint so that the entire butt face is completely fused to the other one. What this 2 means, that's the root. The gap between the 2 plates is 2 millimeters. 60 degrees means bevel, or the groove that we have to grind off to prepare the weld with. They're basically coming weld. And then this little symbol up here, flat, that means grind flush. And especially for architectural situations, to come in and after the fact, well, basically grind the weld down until it's flush with the plate metal. So lots of information in that symbol. The number within the triangle denotes what the spacing between the plates is. Angle in degrees denotes what the preparation face is. CJP tells us we're welding the joint all the way through. Flat bar at the top says we are grinding it flush. PJP is similar, except here we're just, instead of having both sides beveled, we're just going to grind out one side. The root opening's the same. Here is if we've got a 10 millimeter plate, if we're not doing a complete joint penetration weld, we're going to do a partial joint penetration. Note that with a number, some kind, 6 maybe. And basically what that 6 means is we're only going to 6 millimeters of plate, so we might grind it something like that. And then we're only going to partially joint. And then this little curve at the top means leave it as a convex or whatever, bulging out a little bit, so we're not going to grind that weld away. Okay, so we've seen some examples. Triangles mean fillet, V-shapes or whatever, like a skewed V-shape. Or some numbers denote sizes, some denote preparation openings, and fillet welds are generally simple compared to groove weld symbols. Does anyone have any questions about that stuff before we continue on? Katie?
What did you say PJP?
Partial joint penetration weld. So partial joint plate means all the way through the joint. Okay, so well, you generally want it to look something like what's in the picture here. There's a common lingo, I would say, in welding that if you're doing a good weld, they call it laying down dimes. So your weld should look kind of like a series of side to the other with kind of nice, well-defined surfaces. It might not look as defined here. It might be more uniform. Generally speaking, a good weld has a nice-looking surface and it's well-proportioned. Bad weld is anything that the fella at Canadian Tire is doing when they're fixing your exhaust. And so I'm sure someone's seen a weld that looks like this. The MIG weld and fix some exhaust, and you can basically see wires everywhere. All the welds are corroding. They probably didn't even use the gas. So that would be an example of a very bad weld. Okay, so if you want to see a bad Canadian shop, and you'll see what they do there. But there are some different ways to basically decide what makes good weld and what doesn't make it. Good weld looks good, and you'll basically see it. If you're traveling too fast, then you're going to get a lot of spatter. It's going to be too small. If you're going too slow, it's basically going to just molten out, and it's going to have a really big convection, kind of bulgy, and in fact, your lines are actually going to look almost as if they're going the other way. And then there's a bunch of stuff about if the arcs are too long and if the amperage is too high or too low. Those aren't things that are super important to you as the engineer, but you should be able to go up on site and say, that's a good weld, that's a bad weld, and that's not something I can really teach you in this course. It's something that generally comes more with experience. Okay, so that's more of a throwaway stuff, so I'm not super worried about it. Generally, good welds, really bad welds, well, you'd never see that in a structure, that's for sure. And there are some ways what welds are good, and if the weld is bad, what might have caused that bad weld. Most important to the engineer, first and foremost, is the strength of the weld. And so in S16 13.3 tells us the strength of fillet welds, partial joint penetration welds, complete joint penetration welds, and a bunch of other kinds of welds. We're going to focus today on groove welds, And so we're going to look at complete joint penetration groove welds and partial joint penetration. This is the easiest one ever. And everybody knows in the industry that lazy engineers CJP. Because CJP doesn't require any additional work. If you're going to completely fuse the joint through the entire face, then you just basically get the strength of the steel you're connecting back. In the context of our tension member, if you're doing a complete joint penetration weld all the way through the butt joint of these two plates together, TR is the AGFY, Y for that plate that you're welding together. Okay, so that's the factor of tensile resistance shall be taken as that as the base metal, AGFY. Lazy, I don't have to do any calculations for weld. I just know if I specify CJP, I don't have to do additional calculations. On the flip side, they're quite expensive. And so generally, you're going to not do CJP all the time. But it's appropriate to do that in certain situations. If we're looking at partial penetration welds, we actually have to sharpen our... And we're not allowed to exceed, of course, not the fact that we can't do more welding, but the exceed VAGFY. Okay, so if we've got a partial joint penetration weld and we calculate the resistance, we're not allowed to exceed the yield resistance of the strength of the joint. What we're looking at here is a new resistance factor, same beta value, 4.8 volts, lower resistance factor because the variability in the strength and the geometry of welds is more significant. Bolts are old and hot and shaped nicely, high level of reliability. Welds are done by people with different levels of skill. Factor to target the same level of reliability. AN, I'll see clear, but it's the effective area of the fused face normal to the load. Basically, it's the face through the... Dealing with partial joint penetration welds, we're not dealing with the strength of the weld metal itself in this case, even if we have matching electrodes. What we're dealing with is the strength of the base metal itself. As long as we're using matching electrodes, which means a little bit more than the strength of the steel, we don't need to check the strength of the weld material. We just need to check the base metal that we're actually connecting together. Okay? Are there any questions about what goes into this equation? See how it's applied in an example. Okay. Like I said, CJP, you don't have to do any calculations. But if we have a partial joint penetration weld, calculations to figure out how strong this joint is going to be. If we're only fusing some of the face and not... So in this case, we've got a 150 millimeter wide flat bar. So I'm showing this into the page. The width of the plate is coming out of the page at you. That's 150 millimeters wide. This partial joint penetration weld in a butt joint configuration. And what our goal is here is to calculate the factor tensile resistance of this welded joint. Does anyone have any questions about what it is we're trying to do here before we go through the calculations? What's the first thing we need to do here before we can do it? We have to decipher what the hell this is. What does that mean? Can anyone tell me a little bit about what that weld symbol? There's a 2 millimeter gap between the two plates. That's important for the welder doing the work. Not important for us for the strength, but that's a 2 millimeter. What else? Sorry? Yeah, so the degree openings, degrees. What about the 6 here? That's the effective depth of height of the weld. And so we're basically coming in here and we're going to bevel out a little bit here at 60 degrees with weld material. Right, and that's this one. The stuff on the bottom of the line means this side of the arrow. And then we have this. Right, so we're going to bevel out this one at 60 degrees, grind the material away, and come in and fill that with material. So the depth of this weld here is 6 millimeters. Here is 6 millimeters. We've got that on both sides. And so what that it fuses 6 millimeters of the face here, 6 millimeters of the face here, and leaves unfused face throughout the rest of the connection. What do you think these numbers here refer to? Sorry? Yes, that's the length of the weld. And so and generally speaking, if these numbers were left away, they would just be understood that we'd weld the full width. I'm just denoting that here. We're welding 150 millimeters along both sides of the plate. That means that full plate on both sides, right? So this is 150 in the other direction, 150 direction, and we're welding completely across on both sides. Okay? So, once we know what the symbol means in terms of what the joint looks like, now we can actually calculate the resistance with that weld. Okay, so if we're calculating the resistance of this weld, we're using VWANFU. So the tensile resistance is VWANFU. Of the actual base metal. Okay, that's the strength of the plate here. And that's just because it tends to fail the base metal in a fashion something like this. We tend to fracture away. And so for here, it's going to be the 450. VW is always 0.67. In about 20 years, I'm going to have students. And then I've got AN, which is the effective area of the fused face. 6 millimeters of depth on this side, 6 millimeters of depth on that side, 12 millimeters worth of that cross section, and then I've got that 12 millimeters over the 150 millimeter width. Okay, so AN, maybe I'll just write it out here. AN is the 6 millimeters on the top plus the 6 millimeters on the bottom multiplied by the 150 millimeter width. So I'm just going to write that in this case here. 6 plus 6 times 150. FU is 450 MPa. And when I do that calculation, if I can find my mouse here, I end up with a tensile resistance of 542.7 kilonewtons. Okay, so we took VW, which is 0.67. We took the effective fused face on the top, 6 of fused face on the bottom, times the width of the welds, or the length of the welds, multiply that by the strength of the base to get a resistance. Does anyone have any questions about that calculation before we continue? There's one more thing we need to do. We have to check that we're not exceeding the strength of the plate itself in tension. Steel, because why not? We'll also just make sure that we're not exceeding that. So phi A y AG. We've got 0.9. AG is for the plate itself, so 19 millimeters thick times 150 wide. .350 MPa. I don't know if I did that calculation or not. I guess I didn't. It'd be helpful, though, if someone could quickly run that for me so we could wrap things up here in a timely fashion. If I beat you, then that's not going to be... $800. Did I lose my screen there? Oops, I used the wrong value there, 350. 897, I'll call it 898 kilonewtons. Okay, so we end up with 898 kilonewtons. The strength of the actual welded joint isn't exceeding the gross yield area, or the strength in gross section yielding. And so the strength of our welded joint, therefore, is the, I would say, 500 effective fused area of that face. Okay? Any questions about that example before we wrap up lecture for the morning? Okay. Do these things, determine pros and cons of welding versus bolting, differentiate between the different kinds of symbols, and basic weld symbols for groove and fillet welds. And as far as we were concerned for this lecture today, calculate the strength of a partial joint penetration weld in tension. Does anyone have any questions about anything that we talked about? Wrap things up for the day. Or at least wrap things up for the first hour of your day. All right, we'll see everyone then on Friday morning.